right now if you sign up. All right, I have hit the record button. We're going to take a step back. Okay? There's a reason I do pre-work. A big reason I do pre-work. There's also a reason why pre-work's only worth 5 points. I had lots of emails going, we haven't covered this stuff. I have no idea how to do it. Never seen this stuff before. We haven't covered it. I have no idea how to do it. Well, that was a big surprise to me for a couple of reasons. One, pre-work is considered warm-up exercises. So if you think about general physics, one of the things about general physics is, first of all, there's a prerequisite, okay? There's a reason we have prerequisites. And the prerequisite for general physics is called at least college algebra. All right? So the pre-work for chapter 3, I made the assumption that you guys will have seen those types of problems in college algebra. Not necessarily in physics, even though we've kind of hit on a couple of the concepts. Not necessarily in college physics would you have seen the material. You should have seen the material in college algebra. So after about the 10th or 12th person who had emailed me going, I haven't really seen this, my pre-work had done its business. It let me know of a deficiency that maybe through no fault of you guys' own, you guys had never seen the material before. So pre-work does two things. In some cases, my pre-work are going to be vignettes. You're actually going to see a video, and they're going to ask some conceptual questions about the video to bring up terms. This pre-work was more related to stuff that you should have gotten along the way, and not necessarily in my class, to find the level of what people's understanding is. Now, I will tell you that you have seen part of it in college algebra because I actually pulled out your college algebra book. So if you took college algebra at NOC, I went back to your book to look at how your book does it. Only to discover that your book does not use the word vector at all. I went and looked in the index. I went and looked in the chapter that covers the material. Nowhere does your book cover vectors, nor does your book actually refer to polar coordinates. It's interesting because I pulled out a couple other college algebra books. They use the word vector, and they show you polar coordinates. So from that perspective, our book's done a little bit of a disservice. I actually went over and talked to the math faculty yesterday, trying to figure out what was going on, and they went, that's interesting. Well, now we know what we need to kind of emphasize when we hit that chapter. So we've actually talked to the math faculty. So we're going to take a step back, and we're going to look at it. The other place that you may have seen vectors, and you're really going to have to dust off the cobwebs, is high school geometry. Because that's usually the first place that it's talked about, is way back in high school geometry. Also, way back when you're dealing with some beginning concepts way back in elementary school, you may have actually heard it before. So when we talk about vectors, we're going to take a step back, and I'm actually going to do a little bit on vectors today to try and bring you back up to where you're going to go, oh yeah, I sort of remember that. But we're going to use a little bit different terminology. So pre-work did its job in that now I know that I've got to go back and cover some material that I was hoping not to have to cover. But then we're getting there. So number one, when you guys get pre-work, it's not intended to be something that, yeah, you haven't really covered the material, but the idea behind it is to figure out where everybody's level is. That's the first thing. The second thing is to introduce you to some concepts depending upon what type of pre-work it is, which is also why I give you 5 points. So, but then I keep remembering that a lot of you are pre-med students, and therefore you guys are hypersensitive to the fact that if you miss a point, you're just, and I'm going, okay, chill. Okay? Chill. There's a reason why I do 10% 48 hours in advance, so that you guys don't have to be panicking when you hit up a concept that you don't necessarily understand. I do appreciate, though, you guys were emailing me and saying, I haven't seen this stuff before, because that did tell me something that I needed to know. So, we're going to get started. I'm going to switch over to the document camera. I'm mean, cruel, and wicked, but I'm a fair, mean, cruel, and wicked, okay? I'm fair, mean, cruel, and wicked. So first thing, I am going to put up a page in your book. You have in your book this example. This example of one-dimensional motion going up and falling back down. If you want a study guide, I do not issue study guides. Number one, don't issue study guides. Because you have a study guide. Your study guide is your homework. Your study guide is the summary of chapters. Your study guide is your pre-work. Your study guide is your quizzes. So I don't make an additional study guide. But I will tell you that if I were making a traditional study guide, this example right here, you better know. Because you are likely to see, yeah.
We can't see anything on our big screen.
All of a sudden, we lost you.
You lost it.
We can hear you just fine.
Okay, but you lost the document camera.
Yeah, everything just went black.
Okay, I'm going to call the control room because that's not over here, because mine says you should be seeing it. Yeah, this is Frankie Wood Black. I'm in the 8 o'clock general physics. We've got Zoller. It's 112, right, Ken? I'm in Zoller 102. It's Renfro 112.
Renfro, yeah, 112.
Yeah, Renfro 112. I've got on my confidence monitor, I've got that I'm displaying the document camera, but they have a blank screen on their end.
Oh, okay. I'll let Xander and Enid know.
No, they're in Renfro. I'm in Enid.
Oh, okay.
Yeah, the Renfro's the one with the blank screen.
All right. Well, I'll let them know over there and talk a while.
Okay.
All right. Thank you.
Okay, this is going to be a little hard. Talking about vectors and just words is entertaining. But this is example, in your book, it's example 2.8. That's not a bad throw for a rookie. That is the one where he's tossing the ball directly off the top of the building, and then there are various questions associated with it. So you want to make sure that you've got that particular example hands down. The other thing that's going to help you from a study guide point of view is looking at the summaries of each chapter. The summaries of each chapter are going to be really good. Yes, sir?
Could you switch to you real fast and see if we can,
See if it comes back.
yeah.
Well, that was the fun part yesterday. I couldn't switch back to teacher camera at all. I'm going to do this. I'm going to let me do the desktop computer and see if that did anything.
We've got the computer screen now.
All right, let me go to the document camera. The document camera's been causing me issues.
Yeah, we saw the computer screen, but we're getting a blank screen on the document.
Okay, let me do this. I'm going to switch there and switch there. Because that's what seems to be the bigger problem, I think. Usually it's the...
Ah, we got it now.
Okay, cool. All right. Yeah, the document camera seems to be the bugaboo for these rooms. Usually it's in the room I'm in. It's usually, wherever I'm in, we have trouble getting it on the screen. Not the other direction. Okay, so it's this example that you really want to focus on for your study guide. Okay, so let's start talking about vectors. Now, if you go back to your algebra book, you want to go to the chapter on Cartesian coordinates, okay? Because this is where the vector parts start coming from. So if I'm in Cartesian coordinates, I've got my little handy dandy thing there. If I tell you we have a unit vector in the x direction, so this is my x and this is my y, a unit vector is a vector that has a magnitude of 1. And my unit vector is going to be that spot right there. Okay? And my unit vector in the x direction is that right there. And that's where I'm going to use the little I hat for it. My unit vector in the y direction is going to be a j hat. So let's go back, and I'm okay here. It was over in Tonkawa that was the problem, and we've got it up and running for whatever reason.
At any point, was it not showing up here?
No, it was showing up here. What we weren't getting was the document camera on the screen in Tonkawa.
Call him back. I think he misunderstood.
Well, I know he did, and I got it straight. The other thing we got it to fix, just so you know, I switched over on the document cam. We played with it and switched back, and we finally got it to go up right over there.
Oh, okay, so it's good entirely now.
It's good entirely now.
Thank you.
Okay, so let's talk about conceptually vectors before we come back to that. So, anybody pilot? Anybody get on a boat? A sailboat? Okay? When we're tacking, we're dealing with a vector. So if I'm a bird here, okay, so I'm going to be, well, I can draw a little airplane a little bit better. And my little airplane, and I want to go from point A to point B, we're going to fly in that direction. It's just like an arrow. It has a head and has a tail. So it's going to fly in that direction. And we know, because we've had that experience, if the wind is blowing like that, the actual way that this plane is going to fly is like that. We know from experience. Because if I'm driving on the car on one of these roads and the wind's blowing, if I'm not compensating, it's going to blow me right off the road. And that's because vectors are additive, okay? So if this is the actual direction, what's happening is this is the force due to the wind. This is the force that I'm traveling in that direction, which is going to blow me over there. So I can do vectors graphically, and most of us have done vectors graphically. So when I showed on the other day where we had the hockey, or where we had the air hockey puck, right? The air hockey puck was going to the wall, then it bounced off the wall, and its resulting position was a result of adding the two vectors together. Unfortunately, your college algebra book didn't use the word vector, right? Didn't use the word vector at all. So what your college algebra book did was said this: if I walked 3 units this way and 2 units this way, I end up, so there's my 3 units, I end up here at a point that is 3, 2. Well, it's given you a vector. Okay, it's actually given you a vector. It gave you a vector that looks like this. So even though how I got there is I walked here, and then I walked up, and then I walked up, it gave me that point. Some people, depending on their math instructors in high school, may have actually said, I've got what we call vector notation, and write it like that. Because it's describing this line right there. It's describing that line. Well, if it describes that line, what I've been doing is I've been writing it down like this. So if I call this R, here's my R, I can write this R mathematically as 3 times a unit vector in the I, or the x direction, plus 2 of a unit vector in the j direction. It's the same as this. This is just another way of writing it. Now, the rules are that if I want to look at a line that's 3 times this, so I want to look at a line that's 3 times that, well, we know what we got to do. I'm going to add another vector right there. I'm going to add another vector right there. I'm going to go over here 3, and I'm going to end up at 9. So this ends up at 9, and this ends up at 6. And we've done that before. Well, guess what? That's just 3 times 3 is 9. This is 3 times 2 is 6. And I've done it mathematically. Okay? Now, the part that really drives you nuts is this is our good old Cartesian coordinate system. Well, I can actually, this is another R, and this is another R. I can look at this as one big vector here, okay, one big line, and we already know, because we've been playing with it, that I can look at that angle, and now I'm in something called polar coordinates. So instead of doing a representation with an XY, I can represent this with an R theta. And we know how to figure out theta now, right? You know, I can figure out that angle. The tangent of that angle is just going to be my y over my x, and I can actually calculate the angle. And we even talked about it way back in week 1, that if I look at the adjacent side here, this is what we call a projection of the vector on the x-axis. And this over here, which is the opposite, is the projection of the vector on the y-axis. And that's going to become incredibly important when we start looking in 2 dimensions. I'm going to need to know the components of this vector in its x direction and the components of this vector in the y direction. So right now, all I've done, so if I go back to my chapter on Cartesian coordinates, it talks about moving along the x direction. It talks about moving along the y direction. It gives you these points there. And then it also, one of the things that you ended up doing, which was problem 3 on the pre-work, it said, okay, in problem 3 on the pre-work, and I'm going to actually do a problem. So I'm a person standing here. Okay, I'm a person standing here, and I'm going to look at a cow who's sitting right there. Okay? I'm going to look at a cow, and I'm going to actually know where this cow is. That cow, because I can count the fence posts, so I can pretty well tell where that cow is. That cow is at a point 0, 12.5. There's another cow, okay? This other cow is standing at a point over here, and I just happen to know that it's standing at 21.34. So there's one vector, there's another vector. So if I'm going to write this in vector components, cow A is at 0 in the I direction plus 12.5 in the J direction. So I've written it as a vector right there, using the same information, so I can actually write it as 12.5 in the J direction. I can do the same thing for cow B, And it's going to be located at 7.14 in the I direction plus 21.34 in the J direction. And I can look at it and just kind of, just as a reminder, basically I'm adding a vector that's in the X direction, and I'm adding a vector that's in the Y direction to give me that resultant vector. Now, way back when, we learned that the distance between 2 points, this distance right here, we could figure out. And if we go back, what we did is we found that that distance r, and we're going to call that distance r, is just going to be the square root of my 7.14 minus 0 squared plus my 21.34 minus 12.5 squared. And if I do the arithmetic, that ends up being 121.9 meters squared. I take the square root, and that's 11.4 meters. And I know you have this in your college algebra book. It's finding the distance between 2 points. All I've done now is just have written them as vector coordinates. Okay? That's all I've done is written them as vector coordinates. So now let's look at a couple other vectors. So I'm going to start with a vector. Okay, I'm going to start with a vector, and we're going to call it, we're going to do this as a 2 and a 2. So this vector A, I can write as 2 in the I direction plus 2 in the J direction. I'm going to graphically add another vector, but this time okay, and if I start from here, we're going to have this as a vector B, and I make my coordinate system start there. So I'm going to have that go up 3, and that's definitely 2. So this is a 3. So vector B that I have just written is minus 3 in the I direction, and it's plus 3 in the J direction. I've added it head to tail. Okay, I've added it head to tail. This is going to give me a resulting vector, because there's my result, R. And if I look at this graphically, we know that this is 1. And we've got 2 plus 3, that's 5. So I can write this R just from my graph. R is going to equal minus I, because we typically don't put the 1 in front of my unit vector. So I did it graphically, and I got my vector that looks like that. Well, I can do it mathematically. 2 minus 3 is minus 1. I have to add only those things in the X direction because they're independent. And I have to add these in the Y direction. And I get the same result. Now, I don't have to stick with just 2 vectors. I can add a vector, I can add another vector, I can add another vector, I can add another vector, and I can end up with a resulting vector. And I can do it mathematically or not. Okay? And there's some fun things about vectors, which as we get going, we're going to use them a little bit more. But right now, all we're doing is adding and subtracting vectors. We're going to use a couple of rules. So if I do this, so I've got vector A, and I have AX in the I direction and AY in the J direction. And I have vector B, and I get BX in the I direction plus BY in the J direction. A plus B is going to give me AX plus BX in the I plus AY plus BY in the J. Now, if I do A minus B, it's like multiplying a -1 in front of those. And I get AX minus BX in the I plus AY minus BY in the J. If I'm going to do A plus 3B, that's going to be AX plus 3BX in the I plus AY plus 3BY in the J. So I can do it mathematically and be okay. All right. So we're all good so far. Is it starting to make sense? We're just looking at the math. You guys good over there in Tonkawa? Starting to make sense. Okay, now we're going to complicate it just a hair. So I'm going to go back to my picture here. Okay, if I want to know the length of that vector, the length, which is also the magnitude. So that's all we're talking about when we say length. It's the magnitude of that vector. If I want to know the length of that vector, we now know that it's this right here. Well, let's look at my picture here. We know that side's 1. We know that side's 5. That's a right triangle. So a squared plus b squared equals c squared. So in this case, and how we write the magnitude of our vectors, we usually use the little absolute value sign. That's going to be the square root of -1 squared plus 5 squared. So that's going to give me the square root of 1 plus 25, which is going to give me the square root of 26. And I didn't bring my, oh, I have a calculator. Life is good. Somebody left me a calculator. So if I take the square root of 26, oh, and it's one of those. This is going to be 5.1. And if this happens to be, this is 1 meter by 5 meters, if we're dealing with position, that's going to be 5.1 meters. Now the next part is the other weird part, okay? Because WebAssign says, if I'm trying to solve this in WebAssign, it's asking me for this angle right here. It's asking me for the angle that's counterclockwise from the x-axis. So it's asking me for this angle. Now, we've already been doing this already, but the tangent of an angle, so I'm going to call that angle prime, because it's not the same as this angle, is going to be my y, which is 5, divided by my x, which is 1. So if I find this angle, it's going to be that angle prime. So if I take the tangent of 5, the arctangent of 5, it tells me that that's 78.7 degrees. But that prime angle is this one right here. That's the angle I just calculated. So if I'm answering WebAssign's question, I have to take 180 degrees minus my 78.7 degrees. If I do that, oh, I hate that when it does that. That tells me that that's 101.3 degrees. So this angle is 101.3 degrees. The angle I calculated was this angle over there. So when you're working these problems, you have to know which quadrant you're in. Because if I find a vector, so let's do another vector here. So I'm in a Cartesian coordinate system. I've got a vector that's over here. This is going to be, we'll make this 7, and we'll make this 5. I can write this vector r. R is going to be at minus 7 in the I direction, minus 5 in the j direction. I can calculate the magnitude. That's going to be the square root of minus 7 squared plus the square root of minus 5 squared, which is going to be the square root of 49 plus 25. If I do that, it tells me it's 4.19. Nope, that's a cube root. Somehow I got a cube root. I was going, wait a second, that doesn't make sense. That looks better. It's going to be 8.6. The angle that I'm going to calculate is going to be, if I do the tangent, it's going to be minus 5 divided by minus 7. So the angle that I'm going to get is 5 over 7. Gives me 35.5 degrees. But that's this angle right there. So if I wanted to calculate what WebAssign is asking me, because WebAssign is likely to ask me for this angle right here, I'm going to have to do 180 degrees plus my 35.5 degrees. Which gives me 215.5 degrees. So all I've been doing differently than what you guys had in college algebra is use the word vector and write it in a slightly different notation. Because you guys have been doing it for a long time. It's just in a slightly different notation. The reason that we're calling it vectors is because now it has physical meaning. If I walk, I'm going to walk 300 feet in the 300 feet. I'm going to go ahead and do east. Okay, I'm going to walk 300 feet east. We're going to follow a pirate map to marks the spot. Tells you to go 300 feet east from the big tree. Okay. Then you're going to travel 200 feet north. And at that point, you're going to travel 100 feet southwest. We've had those directions before. So what I'm going to end up doing is this. I'm going to travel 300 feet. I'm going to use a black marker. I'm going to have, and everybody knows, right? Never eat sour watermelons. Okay? My daughter remembers it that way. But I'm going to take 300 feet east, so each one of these vectors is 100. So I've walked 300 feet east. Then I'm going to walk 200 feet north. And then I'm going to walk 100 feet southwest. And where I end up is right there, at this lovely point. Well, if I do it in vector notation, so vector 1 is 300 feet in the I direction. Vector 2 is, I'm going to do it over here, plus 200 feet in the J direction. Vector 3, oh God, I got to take care of that one. It's going to be 100 feet because this is a 45-degree angle. Cosine 45 degrees in the I direction, plus 100 sine 45 degrees in the J direction. So now I can add them together. So my resulting vector is 300 plus 100 cosine 45 degrees plus 200 plus 100 sine 45 degrees. If I plug that into the calculator, this actually works out to be 70.7. So does this, 70.7. So this is 370.7 in the I direction plus 270.7 in the J direction. Now, if I want to know its displacement, because where my displacement is, where my start and my finish, right? I want to know the displacement that occurred. Well, I got to calculate the magnitude. And if I do that, that's just going to be the square root of 37.7 squared plus 27.7 squared. Square root 370.7 squared plus 27.07 squared gives me 459. This is in feet. So my displacement's there. Now, if I wanted to find the average velocity, say it took me, since these are in feet, it took me 10 minutes to do this. So I got to figure out seconds. So it's 600 seconds. So my average velocity is going to be 459 feet divided by 600 seconds. It's going to be 0.76 feet per second. Because my velocity is my change in position with respect to time. Now, this right now is in just this overall displacement. This is a magnitude that we have calculated. That's my magnitude that we calculated. Because I actually am not necessarily traveling in one dimension, because we're getting ready to talk about traveling 2 dimensions, which is why vectors are important. But that's a problem that you guys had in algebra. You just didn't do it that way. At least if you took algebra out of the algebra textbook that we have here. You still did things like this. You still did problems just like that. But you did it a little differently. So is this helping? So all those cobwebs from geometry class, way back when, all those cobwebs from college algebra, way back when, and so now for those of you who go, why do I have to take physics? It's because what's going to happen when you get to your senior level classes, your junior and senior level classes, they're going to say, well, remember when you were in general physics and they talked about the force that's being applied? You're going to go, oh yeah, she told me they were going to say that. For those of you who are working on, I took a bone density test yesterday. All right, why on earth would I care about a bone density test? Well, it's a strength of materials issue. So as we all get older, our bones don't necessarily, there's two facts to bone strength, by the way. It's not just bone density, it's bone elasticity. Because if you've ever done it, and we'll talk about Thanksgiving, right? How many of you have broken the wishbone off the turkey? We've all done it. Now think about when I've got the wishbone right out of the turkey on Thanksgiving Day and I try to break it. It's a little different than if I let it dry out and do it a week later, right? That refers back to bone elasticity. So for those people that worry about bone density, yes, bone density does change over age. The question is, does osteoporosis, is it related to bone density or is it related to bone elasticity? Well, in osteoporosis, you're actually losing the calcium in your bones. You actually are losing the calcium. And I have to laugh because my mother, she's older than I am, and she told me, they said that she had osteoporosis. And I said, what do you mean? She said, well, they're telling me my bone density is falling off. Okay, I'll buy that. Your bone density is falling off. And she says, yeah, they're making me worried about it. And I'm going, okay. And I said, didn't you fall off the ladder last week? And she said, yeah. I said, at your age, if you had really bad osteoporosis, it would have broken. What's probably changing is your elasticity, and, it's going to be a little different. So we have some interesting things that you have to look at, strength of materials. But if you're talking forces of blows, well, that's going to be a force problem, and you're looking at strength of materials. We're going to actually do some problems that look at forces associated with like doing a chin-up. And and it'll prove that other muscles are involved. So when you go back into your senior level classes, they're going to refer back, well, you took general physics. That means you're going to have to dust off your general physics book and come back and look at it. So that's why we deal with these kinds of things. So hopefully this makes a little more sense now. And now we're going to do motion in 2 dimensions and why it's important. Okay. What we've been talking about so far is motion in 1 dimension. So I got a car or a truck here. We'll make it a little delivery truck. And we've been talking about that I've got motion in the x direction. Okay? Things we know. One, that in this case, if I am just traveling at a constant velocity, if I'm traveling at a constant velocity, there's no acceleration. Okay? So my little truck, no acceleration, traveling at a constant velocity. Well, let's take an airplane. Here's my airplane, and it's going to drop a package. Here's the ground. Now, my airplane is traveling at a constant velocity. there's no acceleration in this direction. Okay, I don't have any acceleration in that direction. But we've done it enough. We've played with it enough. We've seen it enough. We know that the box ends up over here. So the path that the box travels is like that. We've seen it. We know it. How many World War II movies have we watched where they're dropping the bombs? They're always dropping the bombs before they get to the target. They aren't dropping the bombs at the target. Well, it turns out a couple things are happening. One, if we just drop the box, like we're dropping it from the top of the roof, it should fall straight down. And in this case, there is an acceleration, and that acceleration is 9.8 meters per second squared. Okay? But in this case, you're going, wait a second, what's going on? Well, one thing is, I have a velocity, and we're going to go ahead and say that this is 30 meters per second in the x direction. There is no y velocity. It's only in the x direction. The object's going to continue moving in this x direction independently of what's happening in the y direction. So it starts out over here, and I can actually put it in here. It starts out with a 0 velocity in the y direction. But we know from our problems that we've been working on that if I look at something that I just dropped, as I come down, it's going to end up with a velocity. And my velocity is going to be equal to whatever its initial velocity is with an acceleration times time. Its position is going to equal whatever its velocity is times time plus 1/2 at squared. And in this case, we're going to put that as a y because we're talking about as we're falling here. And we also know that v squared is going to equal initial squared v squared plus 2a times my change in y. Those three equations apply to the x direction as well. That's an equal sign. Because what's happening in the y direction is independent of what is happening in the x direction. The x and y's that are going on in this case, what's happening is independent. The x and the y's are independent of each other. The motion that's happening in the y doesn't care whether or not it had a velocity in the x direction. The motion that's in the x direction doesn't care what's going on in the y direction. So for my x components, I have no acceleration. Those go away. So this distance here that I end up with, my phone's in the way, this distance here is just related to whatever velocity that I started with, provided I didn't have an acceleration in the x direction. But as soon as it leaves the plane, there's no acceleration in the x direction. The only acceleration is in the y direction, and it's going to fall to the ground. So if we know the height of the plane, okay, so let's say that, so we're going to hold that here. We're going to say that our plane is 500 meters above the ground. we can look at things that are happening in the y direction. Well, first thing I know that my velocity in the y direction is going to be 0 when I start. This is my initial y direction is 0. Okay, well that's good. So that means that my velocity at any given point is going to be my acceleration times time, which in this case is gravity times time. My position y is going to equal minus 1/2 gravity times squared. And my velocity squared is going to equal minus 2 acceleration, which is gravity, times my change in y. So that's what's happening in the y direction. In the x direction, my position is going to be my velocity initial in the x direction times time. And then my velocity is just equal to my velocity in the x direction. My velocity squared is just equal to my velocity squared. Because they're independent, if I know how far above the ground it is, I can tell you where the box is going to land, disregarding air resistance. Okay? Because I showed you the ball and the feather problem yesterday, right? Showed you the ball, the Wednesday. In the vacuum, if I have air, those feathers aren't going to, because of air resistance, those feathers are going to behave differently than even the bowling ball. But if I disregard air resistance, I'm going to be able to figure out how far it goes on the ground. Because what happens is this. I know y. That's my 500 meters. I know, and this is going to be negative 500 meters because we're measuring from the plane. I've got 1/2 the acceleration due to gravity, which we know is 9.8 meters per second squared. What I don't know is time. Over here, I'm trying to find. I do know this initial velocity. We said that was 30 meters per second. I don't know time. Way back in college algebra, you had problems like this, and they were called 2 equations, 2 unknowns. I have 2 equations, 2 unknowns. That's t squared, by the way. 2 equations, 2 unknowns. Well, I have all the information here to solve for time. Then I can take that time and plug it in over there. So let's do that. So I have negative 500 meters is equal to 9.8 divided by 2 time squared. Negatives cancel out, so I get 1,000 meters divided by 9.8 meters per second squared is going to equal time squared. Meters cancel, I have 1 over 1 over second squared, so I end up in second squared. This is how your unit analysis is going to help you make sure that you've rearranged your things correctly. And if I do that, so I'm going to get 1,000 divided by 9.8 gives me 102.04 is equal to time squared, that's second squared. Take the square root of both sides. Gives me that time is equal to 10.1 seconds. The distance that I want to find is equal to 30 meters per second times the time that it takes to fall. So that's 30 meters per second times my 10.1 seconds is gonna, my seconds are gonna cancel. I end up in meters, so life is good. It's gonna be 303 meters from where I dropped it on the plane. Two equations, two unknowns. What's happening in the x direction is independent of what's happening in the y direction. So when we talk about two-dimensional motion, so what we did before, so I have my person on the building and throws the ball straight up and it comes straight back down. All right, comes straight up, straight back down. This has been the smiley problem. This is the building problem. We're going to complicate it now. Because instead of just tossing the ball that way, we're going to toss the ball with some sort of x component and some sort of y, or some sort of x component or y component. So if I do this, we know what happens, right? Because we've played with it. Any golfers? Do I have golfers? I got one. Other golfers? Got a couple. Okay. I know I've got basketball players because we do this a lot. If I'm tossing a ball from the top of this building, I can have it land here, I can have it land here, I can have it land there. Because it depends on the angle in which I throw it. Right? Depends on the angle in which I throw it. And what's happening there is, let's take a cannon, just because I can draw cannons, and I'm a military brat. So I have my cannon, and I can send my cannonball off, and depending on what's happening here, I'm going to use my vector, and I'm going to break it out into components. So if I've got a cannonball and it's traveling at 30 meters per second, and we know that we've set this angle at, we'll go ahead and say 35 degrees, I can represent this velocity vector in terms of its x component and its y component. And just like we did with the vectors just a minute ago, I now have the magnitude of the vector, because that's what this is, that's my magnitude. I want to look at its projection on the x component, and I want to look at its projection in the y component. And so this is going to be r cosine of my angle in the I direction plus r sine of my angle in the j direction. And now I can get two independent pieces. So when I start working these two-dimensional problems, the first thing that you're going to want to do is figure out what's happening in the I direction or the x direction, figure out what's happening in the j direction. Because I'm going to need that information. I'm totally going to need that information. Because now if I'm setting this off 30 meters per second, I want to find out how far downrange it can hit a target. And we know what the path looks like, right? We know the path because we've played with it. It looks like that. Now that's going to help us out tremendously, okay? It's going to help us out tremendously because there's my path that it's going to travel. There's some things that I know, okay? There's some things that I know. So let's look at the path that goes like this. So there's my path. I'm going to start out with some initial velocity vector. As I go here, each point is going to have an x and a y component. At the very top, we've got a vx component, but what do we know about the y component? Don't make it harder than it is. It's going to be 0. There is no y component. Just like when I was traveling in one dimension. Just like when I was traveling in one dimension, I'm not going to have a component. So we now know that part's there. The other beautiful thing about this, at least while I'm on a horizontal surface, I have symmetry. The time that it takes to get here is equal to the time that it takes to get over here. Okay, so the time of flight, if I'm on a horizontal surface, is going to be the same. It also tells me what the velocity is just before I hit this point. This velocity just happens to be minus that velocity. These two velocities have the same magnitude, they're just going to be in a different direction. So I can use my symmetry to help me out. I can use my symmetry to help me out. So I can play with these things to do a lot of different problems. For example, I'm standing at the free throw line, and well, that's kind of an interesting free throw, but do I make the basket? What angle and what velocity do I have to be to make the basket if I know how far away I am? If I'm doing golf, here's your factoid for the day. There is no standard, by the way, for golf clubs. If I have a set of TaylorMade irons versus a set of Callaway irons versus a set of whatever other brand name iron you have, the faces of my golf ball head, or the faces of that head, that angle is not specified in the golf rules. It has a range, and that kind of is specified, but it's not specified in the golf rules, so your Callaways are going to have a different angle to their golf heads than TaylorMade's, which are going to have a different angle to the other ones. So your 1 iron and your 2 iron and all of that all relates to the angle at which that they're set at. So when I'm doing that, that's setting the angle to my golf ball, which is going to give me the type of path that I'm hitting for. So for golfers, you guys have been doing projectile motion for a long time. Basketball players have been doing projectile motion for a long time. Baseball players do projectile motion. Soccer players do projectile motion. Horse equestrian jumpers do projectile motion. If you are a hurdler, you have been doing projectile motion. Because ski jumpers are also fun, because we'll actually end up doing ski jumper problems. That you'll have a ski jumper up here at the end of the jump, and they'll come off at a certain angle from the jump, and you'll want to know where they land down the hill. But you can figure out some information, because at the top, the velocity in the y direction is going to be 0, and the velocity in the x direction is going to be whatever the velocity in the x direction was when I started. Because my acceleration is going to be in that direction, and it's going down. The key to these problems is drawing your picture. Right? The key is drawing your picture. So that first problem that I told you that you probably want to look at and make sure you know This one is going to be a similar problem, except now I'm going to throw in an X component to what's happening, and we're going to look at how it behaves going that direction. The problems are going to work very similarly to looking at my airplane dropping things down from a height. Okay, we got it kind of introduced out there, kind of reviewed vectors. So on Wednesday, we'll actually work some more examples. I'm going to stop a little early, so I make sure that people have a chance to come and deal with a few technical issues. And I did get it recorded, so that's going to be better.